For online setting, I have explained some very simple algorithms that share same strategy. Basically, whenever there is some mistake, For instance, xt. So when our pt, the algorithm's pt does not match with the true yt, then the simple algorithms remove or erase all the hypotheses that share the same mistake. Okay, when yt is given to us, we check whether the hxt is equal to yt or not. So collect all the hypotheses doesn't match with yt among our vt hypothesis set, and then erase all the hypothesis h that does not match it with yt from vt and make a new vt plus 1. Since we can erase hypotheses iteratively, in the end we can find the ground truth hypothesis h star. So even if we learn the online learning process infinitely many steps, we have finitely many mistakes when we have finitely many different hypothesis class, or we have finite L dimension. But this simple approach all assume that there exists a ground truth hypothesis H star, and all the alpha yt comes from this H star. Okay, that is called realizable assumption. Without such realizable assumption, the problem becomes more tricky. So is it possible to learn even without the realizable assumption? Well, maybe not. The adversary can always make yt be 1 minus pt. So we can always make yt which is not equal to our prediction pt. Whatever you make, the adversary can make yt so that the yt is not equal to pt. Because there is no realizable assumption, it is fine. There is no such ht, and there is no such hypothesis h that make yt equal to hxt for all t up to current time slot. That is absolutely fine because we don't care. We don't have realizable assumption from now, right? So we have to add some more condition to make some interesting problem setting, right? So for the unrealizable case, people usually introduce regret definition and then add few more conditions so that the regret concept is valid and meaningful. So what is regret? The regret of an algorithm A, which is relative to a hypothesis H, when learning on a sequence of T example is defined as follows. So regret of algorithm A with respect to hypothesis H for time interval from 1 to capital T is equal to supremum of learning instances, all the possible sequence of x1, y1, x2, y2 up to xt, yt, the difference between the number of mistakes by the algorithm minus the number of mistakes by the hypothesis H. So the regret means the relative performance of algorithm A to the given hypothesis H. So the regret is kind of regret compared to a given hypothesis H. So the regret of an algorithm relative to a hypothesis class H is defined as follows. So not a given hypothesis, but with respect to the best hypothesis. Regret with respect to the best single hypothesis. That is regret of an algorithm A with respect to hypothesis class H. Okay, so this is regret analysis. This is regret definition. And so for the regret analysis become more interesting and more valid, we need to add few more assumptions. Why the adversary can make the regret arbitrarily large, like order of t, capital T. So we can make a regret increase linearly to the time slot capital T by simply set yt equal to 1 minus pt. Okay, so for instance, for the binary classification, when our hypothesis class H is either always 0 or 1, 1, 1, and when we make adversary stratis yt equal to 1 minus pt, then the number of mistakes by the algorithm A always capital T, but the number of mistakes by the best algorithm of hypothesis class H is always less than or equal to T over 2. Okay? So the difference, number of mistakes by algorithm and the number of mistakes by the best hypothesis of hypothesis class H is n is T over 2. The regret is n is T over 2. When the adversary can make the output 1 minus pt all the time. When the adversary know which prediction made by the algorithm, and the adversary can set the output yt to be 1 minus pt, then the regret always grow linearly to the type t. Okay, so to be more interesting, we need more assumptions. So this is assumption. The learner randomizes the prediction, which means the algorithm may make pt not deterministically, but make some probability p. So with probability p, the pt is equal to 1. With probability 1 minus p, the output prediction is equal to 0. Like this, we can make the learner randomize the prediction, and the adversary cannot know 0 or 1 outcome by this randomized prediction. So the adversary has to make the yt decision before this coin tossing. Okay, so the adversary maybe the adversary can know the p, but the adversary never know the outcome before write down what is yt. Okay, so whatever the adversary make the yt, there is always some chance pt equal to yt, and there is some chance pt is not equal to yt because of this randomization. Okay, and this simple additional part, because of this part, we can make a sublinear regret. We can make sublinear means the regret does not grow linearly with respect to capital T, but the regret becomes kind of small all over capital T. So when capital T go to infinity, the regret over capital T converts to 0.